Welcome to GenAI Level Up, the podcast where we decode the future of artificial intelligence one breakthrough at a time.
Whether you're just starting your AI journey or you're a seasoned expert, you've come to the right place. Our mission is to make the complex world of generative AI accessible to everyone, everywhere.
In each episode, we dive deep into the foundational concepts, the latest research, and the transformative applications that are shaping our world. It's time to get smarter, faster. Let's level up together.
You know, I had this moment the other day that is a perfect example of why I have this love-hate thing with AI right now. I was trying to sort out a travel itinerary, and I asked this smart assistant a pretty simple question about a restaurant.
Yeah.
I asked, is this place good for a quiet business meeting?
Let me guess. It just gave you the star rating and the opening times.
Worse. It told me, yes, it is highly rated and serves excellent pasta, which, I mean, technically true, but it completely missed the fact that the place is famous for having live opera singers performing at the tables every 15 minutes.
Oh, wow.
Great pasta, yes. Good for a quiet meeting, absolutely not.
And that is the classic AI blind spot, right? It had the data, the menu, the stars, all that stuff, but it completely missed the reality of the situation. It missed the context.
Exactly.
Yeah.
It feels like for all the hype about these models passing, the bar exam, they still trip over the most basic human hurdle, just reading the room. And that is exactly why I wanted to pull this specific research paper for our deep dive today. It's titled Context Graph, and it's from researchers at IDEA Research and the Chinese University of Hong Kong.
It is a really fascinating read. The authors, Chenjin Xu, Muzi Li, and their team are tackling something that I think a lot of people in the industry just gloss over. We're so obsessed with making models bigger that we forget to ask if we're even storing the information correctly in the first place.
Right, and their whole argument is that the way we currently map knowledge, the actual architecture of AI memory, is fundamentally flawed. They want to shift us from knowledge graphs to context graphs, and they've built a new paradigm called CGR3 to actually do it.
It's essentially an attempt to teach machines to stop thinking in these static lists and start thinking in dynamic scenarios.
So before we get to the solution, this CGR3 thing, we really need to understand what's broken. We hear the term knowledge graph thrown around all the time in tech. It's the engine behind like Google's little info box on the side, right? You search Tom Cruise and you get that neat little box with his height, his movies, his spouse.
Precisely. And in the industry, the atomic unit of that graph is what's called a triple.
A triple.
Yeah. It's a very simple structure. Head entity, relation, tail entity.
So subject, verb, object.
Exactly. So for example, Steve Jobs is chairman of Apple.
Okay, that seems fine. I mean, it's efficient. Steve Jobs is the subject, being chairman is the relationship, and Apple is the object. Why is that a problem?
Well, it's efficient for a spreadsheet, but it is incredibly brittle for reasoning. The paper calls out two major failures of the triple: the conflict issue and the completeness issue. It basically strips away the setting. It strips away time, location, and condition.
Give me an example of the conflict issue, because in my head, a fact is a fact. How can facts conflict?
Okay, well, let's use the example from the paper, this hypothetical Mr. A. Imagine your database scrapes two different news sources. Source 1 says, Mr. A stays in Shanghai. Source 2 says, Mr. A lives in Beijing.
Okay, if I'm a human reading that, I just assume he lives in Beijing, that's his home, but he's currently visiting Shanghai for work or something.
Exactly, because you implicitly understand context. You know that stays in usually implies something temporary, and lives in implies permanence. But look at it from the database's point of view. It just sees two triples, Mr. A, location, Shanghai, and Mr. A, location, Beijing. To a logical system, that looks like a contradiction. You can't really be in two places at once as your main residence. A traditional knowledge graph might just flag this as an error, or even worse, just randomly pick one.
Because it flattened the nuance. The triple doesn't have a column for duration or purpose.
Precisely. It assumes a static, universal truth. And this gets even messier with the completeness problem. This is where the Steve Jobs example from the paper gets really interesting.
Oh, right. The timeline issue. This one actually drives me crazy when I use voice assistants.
So we all know Steve Jobs was chairman of Apple, but if you just store the triple, Steve Jobs, chairman of Apple, you lose all the history. He was chairman in 1980. Then, famously, he was pushed out. Then he came back and became chairman again in 2011.
But the graph just sees that one, single link.
Correct. It collapses two totally distinct eras, the startup era of the 80s and the iPhone era of the 2010s, into one flat fact. So if you ask an AI, was Steve Jobs chairman when the iPhone launched? And the graph just says, yes, he is chairman. It doesn't actually know if the dates line up. It just sees that the connection exists at some point.
It's like having a photo album where all the pictures are just jumbled together in a shoebox. You can't tell if the baby picture happened before or after the wedding photo. You just know both photos are in there.
That is a perfect analogy, and this leads to what the researchers call false reasoning. And this is the most dangerous part because it generates these plausible-sounding lies.
This was the part about the ambassador, right?
Yeah.
I actually laughed at this one because it's such a specific nerdy logic trap, but I can see exactly how a computer falls for it.
It's a classic syllogism error. So take Nicholas Burns. He's the U.S. ambassador to China. Logically, where does he work?
In Beijing.
And Beijing is located in
China.
So a standard AI model often learns a simple transitive rule. If person X works in place Y and place Y is in country Z, then person X must be a citizen of country Z.
Oh no, so it concludes the U.S. ambassador is a Chinese citizen.
Correct, because it lacks the context of diplomatic service. It doesn't understand that ambassador is a special role that specifically exempts you from the usual rules of residency and citizenship. It just sees the geographic link and, does the math.
That is actually pretty worrying.
Yeah.
I mean, it's funny with Nicholas Burns, but what if we start using these systems for like background checks or legal research? Sorry, you can't run for president. The AI says you're a citizen of China.
Exactly. It creates systemic errors based on oversimplification. So Zhu and Li are arguing that we need to upgrade our fundamental unit of storage. We need to go from the triple to the quadruple.
The quadruple. So we're just adding a fourth column to the spreadsheet.
In simple terms, yes. But conceptually, it's a huge shift. They are adding a context element. So the structure becomes head, relation, tail, context.
And this context bucket, what actually goes in there? Is it just like a timestamp?
It's much more flexible than that. The paper breaks it down into two main categories: entity contexts and relation contexts.
Okay, let's peel those apart. Entity context sounds like it's about the noun, the thing itself.
Right. Think of the entity context as the unstructured data layer. If Istanbul is your entity, the entity context might include its aliases, like Constantinople. It could include a description from Wikipedia, images, even audio pronunciations.
So instead of Istanbul just being a node ID, like number 404 in a database, it carries its own little biography with it.
Exactly. It grounds the entity in reality. But the relation context is where the real magic happens for solving those logic puzzles we were talking about. This part describes the verb, the connection.
This is where we solve the Steve Jobs problem.
Yes. The relation context includes temporal information, so valid from 2011 to 2011. It includes geographic scope, so won the World Cup becomes won the World Cup, context in Russia.
And provenance. I noticed that in the paper. That feels huge for the era of fake news.
Crucial. The context graph can store where the fact came from. Is this relationship defined by a government tax filing or a random blog post? That source information lives right inside the quadruple.
So if we go back to Mr. A, the system would store. Mr. A stays in Shanghai, context, business trough hotel. And then Mr. A lives in Beijing, context, permanent residence.
And just like that, the conflict vanishes. The system understands that staying and living have different context constraints. Both facts can be true at the same time because the context allows for it.
It feels like we're giving the AI a kind of situational awareness. But here's my question. We've had databases with extra columns for decades. Why is this a new paradigm? Isn't this just better data entry?
If this were just about storage, you'd be right. But the researchers aren't just proposing a storage format. They're proposing a new way to process this data using large language models. That is the CGR3 part of the paper.
Okay, CGR3. This is the methodology. Let's break down the acronym. It stands for Context Graph-Based, Retrieval, Ranking, and Reasoning.
Right. And to understand why we need this, we have to look at the synergy section of the paper. We basically have two main tools in AI right now. We have knowledge graphs. They're structured, accurate, but sparse.
Sparse meaning they have holes in them. If a fact isn't explicitly typed in, it just doesn't exist.
Exactly. And then on the other side, we have LLMs like GPT-4. They are amazing at understanding messy text, but they are very prone to hallucination. They just make stuff up.
So the knowledge graph is the boring but reliable librarian, and the LLM is the creative but maybe slightly drunk storyteller who exaggerates everything.
That is a wonderful analogy. CGR3 is designed to force them to work together. The graph provides the facts, the guardrails, and the LM provides the reading comprehension to understand the context.
So how does it actually work? Let's walk through the life of a question. The paper used a sports example, Kasper Schmeichel, the goalkeeper. Suppose I ask, who does Kasper Schmeichel play for?
In a traditional system, the AI just looks for a direct link Kasper Schmeichel plays for. If the database hasn't been updated since 2022, it might say Leicester City. Or if it has old data, maybe Manchester City. It's a coin toss.
But CGR3 starts with step 1, retrieval. And it doesn't just look for that one link, does it?
No. It performs textual context retrieval. It actually goes and pulls his Wikipedia intro, it pulls recent news snippets, it gathers the unstructured text associated with him. It acknowledges that the answer might be hidden in a paragraph, not just sitting in a database cell.
So it grabs a bunch of potential teams. He played for City, Leicester, Nice, Anderlecht, the Danish national team. Now we have massive options. So step 2 is ranking.
And this is where the context part really shines. A standard search might just return all those teams as relevant, but CGR3 uses context-aware ranking. It looks at the temporal context in the text it found.
It sees dates. It sees things like joined in 2023. It sees left in 2022.
Exactly. It ranks the current status higher because it understands the implied context of the question, who does he play for, is asking about the present tense. It differentiates between a past relation and a present relation.
Which brings us to step 3, reasoning, the sanity check.
This is the most critical step for preventing hallucinations. The model actually asks itself, do I have enough information to answer this reliably?
I love this loop concept. Usually an AI just wants to please you. It'll bluff. It'll just say, sure, the answer is X. This system actually pauses.
It does. If the reasoning layer says, wait, the dates for his current club are a bit ambiguous, it triggers a loop. It goes back to retrieval to find more specific clues. It builds a chain of evidence before it commits to an answer.
That seems surprisingly human. It's like when someone asks you a question and you say, hang on, let me double check that, instead of just guessing.
It is simulating thoroughness. And the results they got with this method are pretty striking. They didn't just theoretically say it works, they tested it against the big dogs.
Yeah, let's get to the numbers. They compared this against standard ChatGPT prompting on some heavy benchmarks like WikiWeb questions.
They did. And on the WikiWeb question dataset, standard ChatGPT, just using, basic input-output prompting, got about 57.7% accuracy.
Which is
Okay.
better than a coin flip, but you wouldn't trust it with your taxes.
Right. CGR3, using this context loop method, hit 78.8%.
Whoa, that's a 20-point jump. In the AI world, people usually pop champagne over a 2% improvement. Why is the gap that big? Is it just about checking dates?
It's the context, but specifically it's how CGR3 handles the long tail.
The long tail. We hear that term in business, but what does it mean for knowledge?
Think of famous facts as the head of the distribution. Who is the president of the US? What is the capital of France? LLMs have seen these facts in their training data billions of times. They've memorized them.
They can answer those in their sleep.
Exactly. The long tail is all the obscure stuff. A local politician in a small town. A supporting actor in a 1980s movie. Specific details about a minor historical event.
The stuff that doesn't have a million blog posts written about it.
And standard models hallucinate on the long tail because their memory is just fuzzy there. But CGR3 doesn't rely on memory. It relies on the context graph. It pulls the specific text description for that obscure entity and reads it in the moment.
So it's the difference between taking a test from memory versus taking an open book test where you can look up the specific page.
Perfectly put. And that is a game changer for reliability. It means you don't need to retrain the whole massive brain every time a new obscure fact happens. You just update the graph.
I want to look at one of the case studies in the paper because it really shows off the reasoning capability, that Obama question. Who was the Secretary of State when Barack Obama was president?
A human finds this easy, but for a machine, it involves checking multiple timelines and then performing an intersection. It's actually a few steps.
Right. So walk us through how CGR3 breaks this down. It can't just Google Obama Secretary of State, can it?
No, because that search would return way too much noise. So first, the system performs context extraction. It pulls up Obama's entity file. It sees President 2009 to 2017. That sets the time window.
Okay, so we have our constraints. The when.
Then retrieval. It looks for the Relations Secretary of State connected to the U.S. government during that broad era. It finds 3 major candidates, Hillary Clinton, John F. Kerry, and Antony Blinken.
Now, wait a minute. Antony Blinken. He wasn't Secretary of State under Obama?
No, but he served in the administration as Deputy Secretary of State, and he's heavily linked to all the same topics. If you just do a keyword match, he scores very high. He is semantically related.
Ah, I see. So a dumber model might include him just by association.
Exactly. But this is where the ranking step kicks in with the timeline check. The system looks at the relation context for each person. For Antony Blinken, the graph shows Secretary of State started 2021. Does that overlap with the 2009-2017 window?
Nope.
So he's discarded. Hillary Clinton served 2009-2013. Does that overlap? Yes. John F. Kerry served 2013-2017. Does that overlap? Also yes.
So the output isn't just a jumbled list of names. It's a filtered, reasoned answer. Clinton and Kerry.
Precisely. It filters out the noise based on time. But there was another example that I thought was even cooler because it involved math, the Apple competitor question.
Oh yeah, which company is Apple's biggest competitor in the global smartphone market?
This is so tricky because competitor is easy. Samsung, Google, Xiaomi, they're all competitors, but biggest, that requires quantitative reasoning.
A standard knowledge graph doesn't know what biggest means. It just knows they're linked as rivals.
Right. But the context graph can store quantitative data in the relation context. It can store market share, 24% for Samsung, 11% for Xiaomi, and so on. The reasoning engine retrieves these numbers, compares them, and identifies that 24 is, in fact, the largest number.
So it's not just finding the answer. It's calculating the answer based on the context data. That feels like a significant leap. It's moving from search to analysis.
That is the core promise here. We are moving toward AI agents that can do actual work for us, plan travel, manage investments, research legal precedents, and those tasks require nuance. If you ask an AI to find me a hotel in Shanghai and it books you in a residential apartment building because it saw Mr. A lives there, that is a failure of context.
Or if I ask it to summarize the legal risk of this company, and it mixes up a lawsuit from 1990 with one from 2024 because it flattened the timeline, that's not just a glitch, that's a lawsuit waiting to happen.
Exactly. Context graphs are essentially giving AI the ability to read the fine print. It transforms the knowledge graph from a static list of facts into a dynamic, reasoning-capable system.
It solves the paradoxes by acknowledging that truth usually depends on when and where.
Truth depends on context. That is the philosophical core of this paper, really.
It's amazing to think that the solution isn't necessarily just make the brain bigger or add more parameters, but simply organize the notes better.
That is a perfect way to put it. Better organization leads to better reasoning.
Before we wrap up, I want to leave you with a thought. We talked about provenance, knowing where the information came from. We're living in an era of deepfakes, AI-generated slop, and misinformation. If we can build these context graphs effectively, could they act as the ultimate lie detector? Imagine an AI that refuses to answer a question because its relation context shows the source is an unverified Twitter account rather than, say, Reuters.
That is a very provocative thought. If we can encode trustworthiness as a context layer, essentially giving the AI a sense of skepticism based on source quality, we might finally solve the hallucination problem for good.
It would turn the AI from a gullible reader into a critical thinker, something to mull over. Huge thanks to the researchers, Jinjin Tu, Muzi Li, and their team for this work. It really feels like a foundational step toward the next generation of AI.
Absolutely. It was a pleasure to break it down.
And to you, listening, thanks for diving deep. Next time you see an AI make a dumb mistake, check the context. We'll see you in the next one.
And that brings us to the end of another deep dive into the world of generative AI.
Thank you for tuning in to GenAI Level Up. If you found this episode valuable, please consider subscribing and leaving a review on your favorite podcast platform. It helps us reach more curious minds like yours.
Join us next time as we continue to explore the cutting edge of artificial intelligence. Until then, keep learning, stay curious, and continue to level up.